Okay guys, so this is the basic fan from Radio Shack. It's $14.99 fan. It's pretty good. It's a Chinese fan. We can see here the specs of it. It's very low amps, actually 0.38 amps, and it's supposed to get more or less like 2000 RPMs, more or less 10%. So actually you'll see that that's eventually the 10% dust stands real. They go for like 1900 and something. And this is very simple to dismantle. We gotta do is just take the rear seal, the rear label off, and then we're gonna find, I already have this one open, we have another seal. We need a small to pop it out, and then we'll see a retaining ring there. We have to take it out, and of course it's packed with grease. It is an open seal. I mean, it's not as a closed O-ring. You can see the opening right there. So try to hook it from the opening. Sometimes you need like 2 screwdrivers, 2 fine flat screwdrivers, and yeah, stuff popped out. Now there is another retainer here, so it's popping out, and then we take it out. So then we have the circuit here. And basically what I like about this fan, it is not like another type. They used old ones, like this one. I already have it off. It's a little bit more complicated as component wise. It's got the Hall sensor, you can see it right there, but then it's got diodes outside and a couple of filter capacitors, but it's got also a resistor there, and it's not that simple. You can see down there 2 more resistors, and the way now they're coming out with this is a much simpler approach, which is just 3 components basically. And this circuit kind of, it's got too much in it, and it's designed for other component type. So basically there are only the 2 filter capacitors and the IC. Now this IC has 4 legs. That's the SDC276, and it's got positive and negative, and then it's got pin DO and DOB. Now what happens here is when the magnet, the rotor, which is a strip of plastic magnet, I'll show it to you. It's simple. It's not, and it's the way it's configured. It's a north and a north and a south and a south. So when it falls into position here, where the sensor senses south, it turns on one of the pins and turn off the other one, and so on. It'll when it's north, it'll turn on the other one and turn off the other one. What I like this is not a reverse circuit. It just switches on or off, and because of the simplicity of it, I'm going to be utilizing this type of simple design. The IC has already built in the protection diodes and the resistor, and it already had the two transistors, which we could not see in there, but they're here. You can see them right there, the two transistors there. Let me see if the light can see it here. Anyway, they are way behind there. You can see the 6 legs there. And yeah, so this is all inside this piece, this IC. And the way that this is wound, I have drawn a CAD schematics on it. It's a bifilar coil. I mean, we can call it, actually it's not a bifilar because it's not connected in parallel. It is just a dual strand of wire. They use a red and a gold. And the way they do it is, so in position 1, these are 2 north and 2 south, and in position 2 is 2 south and 2 north. So it keeps on swapping 2 north, 2 south, 2 south, 2 north, and so on, as whatever magnetic field density it feels, it gets closer to the center of it. Basically, it's the bisector. Bisector is the heavier density, and that's the reason why, if you look at this motor, you'll see there are notches on the spins, on the fins, and on the rotor. Each rotor has like an indentation, which is sinking here, and that creates a bigger air gap on this section here, and a closer to the magnet. So what does, it makes a magnet not sit exactly at the pole, but halfway. And that way we will always, at the time of starting, always have the sensor with the major greater density of either north or south. So it's only a 1 rotation sense. It's protected with diodes inside, so you cannot reverse it. So basically this is it, and we'll be conducting some tests on this. I already had the sensor on reflective tape, and actually because of the speed they go, you don't need to I have the power source already set for 12 volts, and we're gonna hook it here and hook it here, and wait, we have it opposite, and the diode didn't let me go. Good. So now what we have there is 12.6 and 0.26 amps. Now if we get the measurements of the RPMs, we're gonna see 1970. So 1964 approximate. Sorry, you have to read it upside down, but it's the way this machine is set. So yeah, and it's pretty quiet. So we're gonna be building the version, the asymmetric version of this, and this motor is not that because of the IC, it's not that much of a reversing polarity. Actually turns on one sequence. The only thing I don't like about this is that it's distributed all around to close the entire thing in one loop. So there are two loops there, one north-north, south-south, and then another one south-south and north-north, and that's the way it swaps. It keeps switching at very high speed, according to the passing magnet. Now the flux here is the one that actually gets counter when it gets hit on the other way, because it reverses within the same coil, and that's where the asymmetric is, where the symmetric is. The symmetry of the fields, and I'll show it on CADs. It's basically everywhere you look at it is a symmetric deal. So what I did here, I started these. I have shown on the way of winding it before. This is an incomplete motor. I already wound it, and it's 2 pairs only, and this is gonna have 4 pairs. This motor right here has 4 coils, and each coil is a single. So actually, it's got one single coil, you know, in series from pole to pole. It's clockwise, counterclockwise, clockwise, counterclockwise, and so on. And they are all the same way, but the current, when one of the pins gets on, it goes the reverse way. So it magnetizes the polarity the other way around. Now I did this test because I'm gonna be running this motor like this. I'm gonna hold it with my hands, and we're gonna run also another test here. And so this is the same blade, and we're gonna see. I have to hold it before I get it there. And I'm holding it in my hands, and it's about the same. I use the same wire to wind it asymmetrically, and now we're gonna have a reading. It's 2050, 2060. And it's consuming the same. It keeps gaining speed, and you can see how it drops as it keeps developing force. Radiant energy start coming into the off-time coils and stays there, and it's assisting the reversal, the natural reversal of the fields. So you can see with half a motor we got 2180 and 24.24 amps. Now this motor is not even. It is as you can see on the winding, it's not, and this is not hard at all. I mean, this is it. Each coil I mean, each pair has a resistance of 27 to 29 ohms. So basically, it's pretty high resistance, and for the amount of steel laminations that we have, it's not much of a deal. But you can see the position of the sensor is below, because the strip is pretty long, and it covers the area of the sensor pretty well. So it senses there. Now this is a halfway motor. It's only two pairs here. I still gotta do P3 and P4, which will grab each one. This is the north here, and this is the south underneath the red wire. And then P2 is the red wire and north, and the south of P2 is right here. So now I need to start P3 here, north and south here, and then P4 north here and south here on top of P1 north. And that's how we create the spiral of a sequencing spiral. Now I'm gonna finish the winding here, and it is a very interesting project here, because right now we have a motor that goes over 2,000 RPMs. It uses very little, and we can add a coil, a generator coil right there, and see what the effect it does when it rotates, when we put a small load in it. But I'm going to keep winding it, and I'm going to use one sensor, the same sensor, to in parallel feed P1, P2, and P3, P4, like in cross. But eventually the way this motor will run perfect will be with two sensors, two commutators, two switches, like we do on our regular commutator motors. We're gonna have to set. I'm gonna set it at 180, and this is relative. You can put it at 90 degrees either way. All you gotta do is make sure your pins are matching, because they could be reversing, counter affecting rotation, and then it won't move. So basically, I'm gonna do first one test with all like that in parallel, and resistance is gonna be about the same, because it's like adding and dividing by 2, but it's gonna result in the same. But eventually the way I will end up doing it, and I know it's gonna be much better, is with dual commutators, one on top, one on the bottom, and it'll keep on centering timing the ratio of the coils on one side of the all 4 quadrants of it. And then again, this is a modular design here, and it could be expanded into any multiples of 2 and 4. So, and it doesn't need a controller. The controller is just basically the feeding of the speed. It can go faster than just 2,000 RPMs if you keep adding the voltage to this. So it went up, of course, but it's close to 2,000, 3,000 RPM, 2865 at 35.35 amps. I like to keep it to a 0.9 where we were doing the testing. It's my finger touching it. It's 2275. And this is now, it's bigger at 23. Why? Because I accelerated. And now the filter capacitors, what I'm doing, it's only 2.2 50 volt, small little caps. we can in externally we can the caps actually are connected in the output. They are receiving the output, and I'll show it on the circuit, and holding the energy there. In the symmetrical, in the asymmetrical, in the symmetrical, the capacitors are filtered capacitors, but actually what they're doing is absorbing all the spikes when the coils turn off, and it absorbs all the reverse spikes. We could collect them, and we could collect them on a capacitor for per coil, and then take it out, which will be done on further testing and videos.